Howdy class, today we're going to talk about some related rates, and you can find this in chapter 5.5. And one of the first things you will notice about these related rates are that they are very much related to implicit differentiation from the other day. So with implicit differentiation, we always treated y as a function of x, right? Y always equaled a function of x. So we'll put this y equals like that. Now I could have written it like this, but we're just going to go with this nomenclature just because it's a little easier to look at. Alright, so now both variables will be a function of another parameter. Usually time, but not always. And so the other parameter we have in here. So here we got y as a function of t, and we got x as a function of t. Alright, so let's continue on. For the following expression, both x and y are functions of time, and this is the expression we're looking at. We want to find y prime of t. We want to find these as a function of x, x prime of t, and then, of course, t itself. Alright, and keep in mind, since x is a function of t and x prime is also a function of t, ultimately this is a function of t, which is why we express it like this. So first off, let's use some the implicit differentiation, only this time x and y are both variables, or are dependent variables, and the independent variable would be our parameter t. Alright, so we're going to take the derivative of this guy. Note that we got to use the product rule here, so we say x prime times y plus x y prime, and now we're taking the derivative of t. You know, keep in mind this is, we're taking the derivative with respect to t of both sides here. Alright, so it's just 1. Derivative of t with respect to t is 1. Alright, so now what we're being asked is to find y prime of t. We want to isolate that one, so that's what we're going to do. So we have x y prime equals 1 minus x prime y. Y prime equals 1 minus x prime y, all divided by x. And there we go. That is that is our function. And note, I didn't write y prime of t. That's okay. It's implied here. Alright, so this is kind of a general example. The next example will actually be an application problem. Now, I want us to kind of note, we've got this first expression up here, x times y of t. This will work for any functions of x and y that satisfy this expression here. So, for instance, if I said x equals t, well then y would have to equal 1 in order to satisfy that expression. And note that, if you find x prime of t, that's 1, and then y prime is going to be 0. And so if you plug these guys, well, all these guys into the final expression, we note that it will work, right? Y prime is 0, 0 equals 1 minus x prime, which is 1 times y, which is also 1. 1 times 1 is 1. And then x is t, right? So we got our left-hand side. And so that equals 0, which is our right-hand side. Do they equal each other? Yes, they do. Alright, so that was just a quick test. And you can pick any pair of functions as long as it satisfies the original statement. They will also satisfy the final statement right here. So for instance, if I said x equals 1 over t squared, well then y would have to equal t cubed. Multiply these together, these two guys together, you will get t. And then you simply find x prime, which is negative 2t to the negative 3, and then y prime would be 3t squared. And so you plug these guys in to this expression, and you will get that the left-hand side equals the right-hand side. So that was just my quick aside on that one. Let's go ahead. all in blue, so this was just kind of a little bit of extra thing that we did on the side. Example 2. Now let's get to the real life example. The radius of an oil spill, oh no, increases by 20.26 meters per second. That is the equivalent of 30,000 barrels of oil per day. So we want to know how quickly is the area increasing. So first off, we apply what we know. We know that it's increasing more or less in a circle, right? This is the spot of the spill. It comes up, and then the oil kind of flows out in all directions. So we know we're dealing with a circle. And of course, there'll be a little bit of width here. Of course, we're not the question to answer the question. We don't need to know the width, but this is essentially what is happening. So we want to know how quickly the area is increasing. So we want to know area, and we have a circle. What's the equation for the area of circle? Well, it's simply area equals pi r squared, right? That's the area. So a few things to note. The area is, well, it's a function of the radius, but the radius is a function of time, so ultimately it's a function of time. And we also note that the radius is also a function of time. And so what is the rate of the increase, right? dr dt, right? That's the, in units, that would be radius, which is in meters. Per time, right? That's what's going on. That's our dr dt. Well, that's going to be 0.26 meters per second, right? Those are the units that we are dealing with. All right, so now we're going to use our derivatives, for rates, right? We're taking the derivative of both sides with respect to t. All right, so d dt dt. That's what's going on. All right, so this is just simply a prime, right, as a function of time. And then over here, we've got a constant 2r. You don't stop there because we also need to know dr dt, that is r prime. No, we already know what r prime is. And so this is going to become, right, it's 0.26 pi 2r. And so that equals 0.52 pi r. All right, so we've got a prime. It's we have it expressed as a function of radius. We're just going to leave it here for right now. Like I said, even though it is a function of the radius itself is a function of time. So ultimately, the a prime we've discovered is a function of time. What if we wanted to know real fast what was going on when r was 1 meter, right? That would be, when is the radius of the spill 1 meter? Well, you just plug that in. My cat says hi. Plug 1 into there, and so it basically becomes 0.52 times pi. And a decimal equivalent of that would be, so this would be about 1.63 square meters per second, right? That's how it would be increasing. Because what is a prime? Well, that is, dA with respect to, right here. And so what are these in terms of units? Well, that's, the square meters per second. No. Okay, so let's go on to the next example. Oh, and one more thing, it is possible to find what the function of t was, but that is going to be a issue for another section. It involves antiderivatives. If you're looking ahead in the chapter of contents, that is something that is going to be coming up later on in the course. All right, so now we're going to look at a slightly different example, slightly different, but also slightly the same. We have water entering a balloon. So before we had kind of a dark example, when things go really bad, but involved a circle, which is a conic, but this one also involves a conic, but instead of being a two-dimensional circle, it's going to be a three-dimensional sphere, right? That's what a balloon is. And so we've got a faucet. We've got some running water coming out of the faucet into our nice big red balloon. Like so. Alright, and we want to know, how the radius changes with time, right? How much does that radius change with time? Here's our, our basic sphere. All right. So we have a volumetric flow rate. Oftentimes you'll see the letter Q to represent that. But we're just gonna use the V for volume. But Q does happen a lot. But we don't have V. We've got V prime, right? We've got the derivative, and so that's 10 cubic centimeters per second, right? Change in volume per change in time. That's what we have right there. All right, so what is the equation for the volume of a sphere? Well, the equation for the volume of a sphere is 4/3 pi r cubed, right? And so we're going to use a little bit of implicit differentiation. We want to make sure that we are well aware of the fact that volume is a function of the radius or time, and that we also know that the radius is a function of time, right? Everything ultimately is a function of time. And so we're going to go ahead and calculate this through. Take the derivative of this equation, so we have 4/3 pi times 3r squared. We're not done. We got to include r prime. And again, now what is r prime? R prime is dr dt, right? That is what we're after. That's what we want to know. We want to know how the radius changes with time. Well, that's what this expression is. All right, and then we also know that v prime is 10, and so that's what we're going to put right there. So we've got all these things. Let's go ahead and calculate through, or solve for r prime, should I say. So we have 10 equals, so 3's cancel there. Let's go ahead and just have that stated from the beginning. 4 pi r squared r prime. And now we're simply solving for r prime. So r prime is 10 divided by 4 pi r squared. And we can simplify that down to 5 divided by pi r squared. And that's it. That's our answer, right? We'd have to go a little further if we want it strictly as a function of time, but we get it as a function of a radius, which we're given is a function of time, so this is good enough. So, quick question. What happens as our radius approaches 0? And note I've got a little positive sign because we can only approach a radius of 0 from the right. We cannot approach it from the left. A sphere cannot have a negative radius. So notice that as the radius approaches 0, what is happening with the rate? That is the limit as the radius approaches 0 from the right of r prime. What does that become? Well, that's going to be 5 over pi, and then, 0, so it's some, really small positive number that we're just calling epsilon. Well, that's approaching infinity. So as your radius approaches 0, this whole thing is feeling really fast. What this says is that initially, when the radius of the balloon is small, because note the radius will never be 0, because if you look at a balloon, there's always a little bit of something in there. As we get closer to that point, the beginning, should I say, the radius of the balloon will be increasing very quickly, and as the radius gets larger, what happens? Well, from experience, we know that the sphere of the balloon gets shorter and shorter. So what happens as the radius approaches infinity, that is r prime, we're taking what happened as the limit approaches infinity, that is like a really long time out. Like the radius gets larger. Well, then this is going to be 5 over pi times infinity, which is, a really tiny number, which we'll just call 0, right? So it's pretty consistent. When the radius is small, the balloon fills quickly, and then as the radius of the balloon gets really large, it increases slower and slower and slower. And so note the limits of the balloon. I want us to kind of think a little bit more critically about this than in terms of what these equations might suggest. This equation that we have here, it's not valid when the radius is 0, right? Because a balloon can't have an infinite rate. So the domain of this guy, we'll put 0. But what's in the upper domain? Can we have an infinite radius? Well, no, that doesn't make sense. It would be the radius at which the rubber or plastic in the balloon breaks, right? Because it won't go beyond that. So we'll just say from 0, from the R break, where that stands for the breaking point of the balloon. And we can include that point or not include it, whatever. But that's how you would set that up. We're just going to go ahead and include it because we're going to say it is going up to that point, but once it breaks, it's done. Okay, so now we have our last example. We have a 20-foot ladder that is sliding down a wall. Here is the setup. We've got our wall right here, and then we've got our ladder. We'll make it a blue ladder. Why not? There's our ladder. And so it is sliding down the wall. This is a rigid ladder, so it's sliding down the wall, sliding down. Well, then it also must be, the bottom's going to be flying out. All right, so we've got this bit of information right here. 2 feet per second. It is moving away from the wall. So that is moving away from the wall at 2 feet per second. And we want to know how quickly is it falling. We'll just call that v. Now, note we can overlay x and y coordinates. Right, this would be our x coordinate. This will be our y coordinate. So that this point right here, that would be our x, and this point right here is going to be our y, right? The y coordinate of the ladder. And this is a rigid ladder. Okay, and let's go ahead. That dot represents the origin of our axis to coincide with the corner of that wall. All right, so we've got x squared plus y squared. This is the Pythagorean theorem, right? The one leg squared plus the other leg squared equals the hypotenuse. And what is the length of this ladder? It's 20 feet. There we go. All right, so this is going to be our function that we jump off of. We're going to be taking the derivative of this guy. So let's go ahead and take everything. I want you to keep in mind that x is a function of time, and y is also a function of time. This is very important to keep in mind. Y is not a function of x, y is a function of time, and x is also a function of time. So we take the derivative of this whole thing. We get 2x times x prime plus 2y times y prime. And then the derivative of 20 squared is 0. All right, so note there are some things that we already know. We already know the x prime. Right, that's this guy here. So that's going to come in right there. Y prime, that's an unknown, but we're calling it v. Okay, and so also note we can cancel this 2 and this 2 out since we've got a 0 over here. All right, so let's go ahead and plug everything. We got x times 2 plus y times v, and that all equals 0. All right, v is our velocity as it travels down, so let's solve for v. V equals 2x divided by y, negative. Now we can leave this in terms of x and y as we have. Note we could also solve this first equation for x or y and plug it in, so that way we have the velocity in terms of just one variable. Let's go ahead and do that for a second here. Let's go ahead and make it as a function of y, since we're looking for the downward velocity. So we're going to go ahead and eliminate the x, and so go ahead and have x equals the square root of 20 squared minus y squared. Note that I am not going positive or negative because it really doesn't make much sense to include the negative, because the negative would imply a distance over here. We know the ladder is sliding this direction, so we just totally discount this altogether. And so let's plug that guy in. Right, that's our value for x. We're going to go ahead and plug that in right there, so that we have negative 2 times the square root of 20 squared minus y squared, all divided by y. All right, and that's it. That's our expression. So, for instance, are we dealing with feet? When the ladder is 1 foot above floor, because keep in mind that we're measuring from the origin up. When we are 1 foot above the floor, if you plug that in, how fast is it going? You just plug one in, so we have negative 2 times the square root of 20 squared minus 1 squared, all divided by 1. And so it becomes negative 2 times the square root of 399 all over 1. I'll leave that off. And so when you work this, plug it into the calculator, you will get negative 39.95, and that would be feet per second. All right, so a few things. Why is there a negative sign? The negative sign is there because your velocity is downward, and it'll be traveling at negative 39, or about 40 feet per second downward. You don't want your foot underneath that ladder when it falls, because particularly if that ladder has any weight to it, it's going to hurt. All right, so one other thing. How fast is this ladder traveling when you're 20 feet above the floor? I want us to think about this before we do any math. What does it mean when it's 20 feet above the floor? How long is this ladder? It's 20 feet. So if you're the top of the ladder is 20 feet above the floor, it means the ladder is straight up. It's not coming down. Its velocity should be 0. Experientially, We should be able to intuit this. So let's plug this into our what we have here. When the velocity equals, this is, when y equals 20 feet, you plug that in, we get negative 2 times the square root of 20 squared minus 20 squared, all divided by 20. Well, 20 squared minus 20 squared is 0, and so 0, as we would expect. How about when the ladder is about to hit the ground? How will we find this? Well, when you hit the ground, how far are you above the ground? You're not anything. Your height is 0. That is, y will equal 0 feet. So you plug that in, and you get the velocity equals negative 2 times the square root of 20 squared minus 0 squared, all over 0, which causes you to have a divide by 0 error, which we cannot do, and so therefore when it actually hits the ground, we've got a divide by 0 error, so we cannot include that in the actual domain for the problem. Have a good day.